Warm-up problems from today's face-to-face class. We spent the majority of the time today looking at converting fractions to decimals and decimals to fractions, and had a few examples. Started off with this one, which is pretty straightforward, 2/5, and it was a way to illustrate that we have two general methods when we have a fraction that is going to have a decimal equivalent. How do we determine that? One way is to simply do the division, 2 divided by 5, and you'll notice that we set that up and we wind up getting 4/10 when we do the division. The other method that is mentioned in some of the slides is if you can find a way to convert the denominator of your fraction to one of the values that you find in the decimal place values, 10, 100, 1,000, and so forth. You can use the idea of converting that denominator to, in this case, a 10 by multiplying by 2, and you also must multiply the numerator here by 2. And we say, wait a minute, what did all that do? I just got another fraction. Well, you do, except what you now have is you have 4/10, and so think about that for a little bit, and you're going to agree that 4/10 is another way to say 4/10. Now, the other problem is if you're given a decimal and you're trying to go back to a fraction, if you have a terminating decimal, how can you do that? And you say 40 hundredths. And what did I do then? I simplified this fraction to 4/10, and I further simplified back to 2/5. So in essence, what you wind up doing is you wind up setting up the decimal as a fraction with the denominator, the decimal place value digits. So in this case, since it was hundredths, it was 40 over 100. Had I given myself 4/10, I would have said 4 over 10. Had I given myself 400 thousandths, I would have said 400 over 1,000. And so at any rate, whenever you simplified any of these three, you're going to get 2/5. Convert fraction 1/3 to a decimal. Again, we're just going to divide. Why? Because there's no way I can multiply 3 times a whole number and get 10. Think about that for a minute. 3 times 3 is 9, 3 times 4 is 12. I can't get to 10, or 100 for that matter. So what I did is I said, let's divide it out. This is an example of getting a repeating decimal. So if you look in your calculator, for example, and let me get my calculator out here. If you just look in your calculator at what you get when you do that division, you're going to get 1 divided by 3, which is 0.3 repeating. Notice that it stops here because the calculator just doesn't have any more room, but this would go on forever. Now, how would we write that? We would write that with a little bar symbol right above it, and that indicates that this is not just 3/10, it's actually 3 that repeats. Now, this is a more challenging problem. How do you convert a decimal? And I guess I'll just say here, this really is a special case. This is a repeating decimal. Wait a minute. Repeating decimal, what does that mean? It means one of these where the decimal continues to repeat. The other kind is a terminating decimal. So what does that mean? Well, let's try one. 2 divided by 5, decimal terminated. Do we need another one? Oh, what about 3 divided by 4, 3/4, 0.75. So you see the decimals are ending. That's as far as we can go. Said differently, when you divided this one out, if you said 3 divided by 4, you're going to come with a remainder of 0. So whenever you do the division process, if you can't get to a remainder of 0, notice up here we got to a remainder of 0. I know this is a terminating decimal. This one I will continue to divide forever. I will never get to a remainder of 0. So that tells me I'm going to have a repeating, not a terminating decimal. Think about that for a second now about the significance of this. So there are some decimals that when you try to convert them back to fractions or vice versa, you're going to have a bit of a challenge on your hand. So how do you convert a repeating decimal to a fraction. Well, there's a technique that is pretty clever, and I demonstrated it with this particular one. So what you do is you have to do a little work that might be slightly above the scope of this class, but it's not that hard, so we can all get this. You define a variable or a value. Just don't get too complicated. This is just a value, and the value I'm dealing with is that. So I'm just going to call my decimal point 3 that repeats that. Now I'm going to do a couple of simple things. The first thing I'm going to do is I'm going to multiply this by 10. And to keep equality, since I said this equals that, to keep equality, if I multiply by 10 here, I got to multiply by 10 on this side. Notice what happens. When you multiply this value by 10, the decimal point moves one place to the right, and in effect, you have a whole number here now, and your repeating pattern still exists. It still exists as it did before. Then cleverly subtract x, 1x. Leaves you 9x. Oh, wait a minute. I'm going to subtract on this side, not x, but I'm going to subtract the equivalent value. And notice it subtracts away the repeating pattern part, and I'm left with 9 times x is equal to 3. So what was I trying to do here? I was trying to come up with an equivalent form for just x. So if I have 9 times it, how can I get to just 1? Well, divide by 9 and divide by 3. And when you didn't see this, you'll say 3/9 simplifies back to 1/3. So we've accomplished what we were trying to do with converting a repeating decimal to a fraction. Now, here's one that's more complicated, and we actually did this one in class. So the fraction 2/7, if you divide 2 divided by 7, let's see what you get. You're going to get 2 divided by 7. You get this pattern. Now, on this calculator, because it only has a space for 10 digits, you're going to see that I got 2, 8, 5, 7, 1, 4. Now, notice, right here, it looks like it's picking back up 2, 8, 6, because it can't go any further. It doesn't have room. And all it simply did was it said, hey, there should have been 5, 7 here, but I let 7 round the 5 to a 6. So you can't see that it's a fully repeating pattern, but you can maybe, if you want to do some long division and play around with this for a little while, you would see that the pattern that repeats is 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, 1, 4, 2, 8, 5, 7, 1, 4. So the point of this is that sometimes the repeating part is not a single digit. Sometimes it might be several digits, as it is in this case. So there's our decimal equivalent. Now this problem is more of a challenge, because if I ask myself, how can I convert this back to the fraction 2/7? Now I know it's 2/7 because that's where I started from. This one's harder, and you have to think the same process that we used over here. So notice we set it up the same way, but I was able to multiply by 10 here to get the repeating part moved over to the right of the decimal place. Here, I need to multiply by a much larger value. Why? Because I've got to move this decimal point not 10 places, but 6 places. 1, 2, 3, 4, 5, 6 places. So I'm going to have to multiply 1,000,000 times x and 1,000,000 times that just to move this decimal point to here. Oh, the repeating pattern is still here. It didn't go away. It's just now extended beyond the decimal point. Same trick. Subtract 1x. Subtract an x on this side. I'm now left with this. 999,999 times x equals to this value. How do I find what x is? Here's my fraction. 285,714 divided by 999. And you say, am I supposed to simplify that? Yes, you are. It's a fairly tedious process. And what we wound up doing in class is we wound up doing some prime number factoring. So we factored and got to here. Got a little concerned because I couldn't see how to go any further from here. So I said, well, let's don't quit. Let's work on this one. We could have worked on either one of them first. I started on this one. Factor, and lo and behold, notice what comes out here. So you ask yourself quickly, what is the significance of finding this value, 5,291, 5,291, in both of these factorizations? Hint, hint. The greatest common factor is 5,291. Now, I promise you, it'll be hard to determine that without factoring, the prime number factorization. But once you find it, it turns simple. You divide out that greatest common factor and you get 54 over 109. You can factor that one more easily, cancels out, and you come back to 2 sevenths. So this was a fairly complicated, tedious problem, but we do now have a method. We have a method for converting a fraction to a decimal and a decimal back to a fraction when we've got a terminating decimal. We also have a method for converting fraction to decimal and decimal back to fraction when we have not a terminating decimal, but a repeating decimal. All right. Now, we also spent just a little bit of time on this idea of ratios and and we said, hey, here's a collection of shapes. How can you describe these using ratios? And we made the point that up until this discussion, we've always said that when we have fraction notation, it has a specific meaning. This is how many it takes to make the whole, and this is the number I have. When you use ratios, you can use ratio in fraction notation form to specify nothing more than a comparison of two quantities. So, for example, I can describe this group of shapes, not completely, but one way to describe it. It's not a complete description, but it's a way, is to say there are 3 of these rectangles to 2 of the triangles. Can't argue with me on that. 3 to 2. 3 colon 2, or in fraction notation form, 3 to 2. Now, one of the keys to ratios is to make sure you understand what quantity you're comparing to what quantity, to specify the quantities. So if somebody said compare triangles to rectangles, I would just turn this upside down. I'd say it's 2 triangles to 3 rectangles. Another one was circles to triangles, 2 to 2, and the other one here we did was rectangles to circles. There's nothing complicated here. This is just a demonstration of how we can compare quantities and use ratio notation. And the 3 forms are the word to, a colon, and fraction notation. Now we're going to use this one a lot because we can take advantage of some of the arithmetic we learned about how to manipulate fractions when they were treated as fractions. This is a ratio in fraction notation form. So I'll slide that over there for you to look at that a little bit. You might pick yourself a repeating decimal sometime and see if you can master this technique. And then here's the factorization that we finally got back down to 2 sevenths for this problem. Okay, so I think I'll stop here.